So now I'm going to show you potential energy used within our everyday life using this soda can. I'm going to apply kinetic energy, which is shaking the bottle, causing the potential energy within the bottle to increase, and then I'm going to release the energy by opening the soda can, causing the energy to be released. Now the energy is going to become stable. It's going to become stable. Oh, this is so nasty. Cut. So now I'm going to explain the potential energy curve of the soda bottle. This is the initial step, that's where the kinetic energy was applied, causing the potential energy to increase within the bottle, causing it to be unstable. At this point, that's where it was the most unstable, and that's where I removed the cover to release the energy, causing the potential energy to decrease, causing the substance to become stabilized. Because the product and the reactant was the same, it caused our equilibrium constant K to be equal to 1, which caused our delta G to be equal to 0.
Okay, this is how potential energy works. Let's say we have an atom, boron, right here. In this cloud of valence electron, it has 3 valence electrons, which is most comfortable. However, it can hold an extra electron. So let's say I'm forcing myself into this circle, right? I make myself into this circle. Now we repel. The potential energy was at its lowest point, but now since I came in the picture, now the potential energy is increasing. Therefore, I want to leave. They don't want me here, and I don't want to stay here. So my potential energy is increasing. So let's say I have a positive charge. Positive charge is over there. And I'm getting closer to that. I'm being attracted to it. So I can easily leave here. And meanwhile, their potential energy is going down again, back to their normal state, while my potential energy is going towards this positive charge. And the closer I get, the potential energy decreases. And when it's close to it, closest point, it's at its most stable. So that's potential energy.
So as you can see, right now we have 2 different molecules. We have CH3Br and we have H2S. So the first thing that we're going to do is display the lone pairs, because they're not currently displayed here. So Br being a halogen will have 3 different pairs of lone pairs. And sulfur will have 2 pairs of lone pairs. The next thing that we'll do is find the partial charges of each atom. So bromine being a halogen, and the fact that it's more electronegative than C, will have a partial negative charge. Carbon, being that its electrons are attracted to the bromine, will have a partial positive charge. And then the 3 H's will also have smaller partial charges. In this molecule, sulfur will have a partial negative charge. Hydrogen will have partial positive and partial positive. So now that we have all the partial charges displayed, we have a better idea of what will attack what. So in this case, we will make it so that sulfur, being the partially negative, will attack this carbon, which is partially positive, like I said before. So when we're drawing the arrow from these 2 lone pairs over to this hydrogen, we're going to make sure that we don't go through here, like most people think, because there's too much repulsion there will be too much repulsion between the bromine and the sulfur. So we're going to just have to come right around here to the carbon. So when this occurs, you'll see that there will be too many bonds attached to the carbon. It already has 4. With this sulfur adding onto the carbon, it would make 5, which would be 10 electrons, which is way too much for the second shell of carbon. So what will happen is one of these atoms will have to leave. We're going to make it so that bromine is the one that leaves. So I'm just gonna make this arrow right here. So it's taking back its electron, plus one more electron, making it negative. Yeah. Which will make it so that carbon, once again, has 4 different bonds. Okay. So what we'll notice is that as this molecule gets closer to this molecule, the potential energy will decrease, being that there's an increase of attraction between this partial negative charge and this partial positive charge as they get closer and closer together, which means that the overall stability of the entire molecule will increase. So this is how the product of these 2 reactants would look like. As you see, there would be a new bond created between the carbon and the sulfur, and then there will be bromine by itself. It'll be a negative electron due to the fact that it gained both electrons from this bond. Yeah, this is how it looked like. And then sulfur, of course, would still have its own pair because we only had 1 lone pair. So when you compare the reactants to the products, you'll see that the reactants are actually more stable based on the fact that there's no charges. Whereas this BR, even though it's pretty stable on the BR, because the BR has a big shell, it's still not as stable as this, being that this is a neutral molecule and this is a neutral molecule. So based on that, we can assume that this reaction is endothermic. Yeah, meaning that K would be less than 1.